And it started. Hello, everyone. My name is Jacopo Poli, and I'm the lead of machine learning at LightOn. LightOn is a startup based in Paris, in France, and we build hardware for machine learning using optics. And we organize these LightOn AI meetups since a few years, and since 1 year now, I think they are online because, reasons. Um, and this is the 11th event that we organize. And for the 11th event, we have Douwe Kiela from Facebook AI Research. I see he's saying I'm pronouncing it correctly, so that's great. And he's going to be talking about his work with Shengshen, Alexei Bevsky, Harry Morkos, Kurt Koitzer, and Michael Auli. I don't know if I pronounced these ones correctly, but hey, on reservoir transformers. So without further ado, I leave the show to you, Douwe, and thank you very much for accepting the invite.
Yeah, thanks, and thanks for inviting me. It's always fun to do these sort of things. So I should say most of the credit for this work goes to Shengshen, who was my intern over the summer. So he did a lot of the work, and I'm just presenting it to you. That's, I guess, my role in this. All right, so going to be talking about reservoir transformers, and transformers. If you have been working in machine learning or AI or NLP or computer vision, you'll know that they're underlying this sort of revolution that's happening in the field. So in NLP, we've seen things like GPT 1, 2, and 3, and BERT, and the Sesame Street models, whatever you want to call them. And they've really changed the field for the better. And what's really underlying the changes that we're seeing is huge quantities of data and huge quantities of compute, and this new architecture, the transformer. So there's a lot of excitement about this, and what you see happening now, for example, is that in computer vision, people are also starting to switch from convnets to transformers as the sort of future of the field. But transformers also have some very important limitations. So one of the main limitations is that the self-attention mechanism in a transformer, so I won't have time to explain in this talk what a transformer is, so I'm just assuming that you sort of at least have an idea of what it is. But one of the problems is that the self-attention mechanism is quadratic, which means that it's very hard to scale to longer sequences, for example. And if you want to go very deep, then these are just very expensive computations. So one question is, how can we make transformers more efficient, and how can we scale them better to more data? So that's one. The other question is, what do these transformers actually learn? So there's this sort of cottage industry happening now in NLP, where people are doing what they've called BERTology, which means trying to understand what these BERT models learn by inspecting, for example, what layers actually represent when you train linear probes on top of them. So that's another interesting research direction. And this work is at the middle of these two interesting questions. So in the basis, the idea of this work is almost embarrassingly simple. It really is. So if you know how neural networks work, you do a forward pass, you compute some gradients using your objective function, then you backpropagate the gradients, and then you apply the gradients. So the only thing that we're doing here, so this is like, we have our parameters that we update with the new gradients, right, with some learning rate. And the way we compute all the gradients is by using essentially the chain rule. What we do here is we do apply the chain rule, so we backpropagate all the gradients, but we do not apply all the gradients. So for this layer here, which has a different color, we're keeping it frozen, randomly initialized. We never update it, and it's just a random projection. And so the idea here is that if you do that, then you're more efficient because you don't have to do this matrix addition here, right? So if you scale this to very large matrices, then this will make you more efficient. It might actually work quite well. So I've done some previous work where we showed that a random LSTM on top of pre-trained word embeddings, so these were, for example, glove embeddings. If you have a random bidirectional LSTM, you just keep it fixed all the time. You train a linear classifier on top of that, then it actually works surprisingly well. So the goal of that work was not necessarily to get a new state of the art. It was just to make sure that we understand exactly what our networks are learning, and to have a very solid baseline, because it turned out that these random sentence encoders work really well. So the first thing you should do if you have a network and you want to evaluate how good it is, you should compare it to its random initialization where you only train the final layer. So that, I think, is a very important baseline to keep in mind in a lot of NLP settings, because often people make it look like their model is a lot better than it actually is, just by virtue of the scale of the parameters, for example. And of course, this is a super old idea. I mean, basically, it's the idea that underlies the kernel trick, where if you project to a higher dimensional space, then it might be linearly separable. So that even applies if you have a random projection to a high dimensional space. So the Johnson-Lindenstrauss lemma is an instantiation of that. There's this very nice paper from Thomas Cover where he basically shows this already. And then more recently in the SVM literature, you have the work of Rahimi and Recht, where they sort of reinvent this. And then I guess me and Jack Whiting also reinvented that again, and then discovered that it has a long history in the machine learning literature. And so another famous instantiation of this idea in machine learning is so-called reservoir computing, where you have a fixed random recurrent neural network, which is called the reservoir. And then there's a readout function on top of this, which you actually do update. So this, yeah, the sort of group name now is reservoir computing, but the papers that started this are echo state networks and liquid state machines. So these two papers here on the slide that started this. But again, this is sort of just an instantiation of these old ideas that go back to Thomas Cover. And if you look at the literature in 1962, there is a person from Italy called Gamba, who is already training a Gamba perceptron, which is just essentially this idea. So a random projection with a linear classifier on top. All right, so the goal of this work here is to use all of this knowledge that the field has to see if we can try to speed up transformers by doing this freezing and keeping fixed of these reservoir layers. And hopefully we can do this speeding up without sacrificing too much of the task performance. So ideally we become faster, but we don't sacrifice performance. And so there are a lot of ways you can examine performance here, and I don't think that there's an agreed upon way to do this in the community yet. So what we propose in the work is the area under the convergence curve, as we call it, the AUCC, where F here is just your network and G is your evaluation metric, and then you're just integrating over time until some point where you say that all networks are converged. So if your T hat here, if that is a small value, then this metric doesn't make a lot of sense. But as long as you make sure that it's sufficiently big, then essentially the network that is the most high performing on the evaluation metric over time is the one that wins. So that's exactly what you want to get at. But we're also looking at the training time until you reach your maximum validation performance. So how long does it take you to get to your max before you start overfitting and you go down? How well are you generalizing on test set data, and how many trainable parameters do you have? So these are a couple of different ways that we'll be looking at these networks and trying to do comparisons. So we're going to evaluate this idea on a bunch of different tasks. So we wanted to have a good range of different ways of examining this question. So on machine translation, we're doing IWSLT and WNT. So these are like a smallish kind of data set, IWSLT, which you can train on one single GPU, which is nice. And then on WNT, you have a larger data set, so you need more GPUs and more time. And then language modeling and Wiki8, which is even bigger. And then we're also doing this Roberta pre-training. So these mass language models like BERT and Roberta have really revolutionized NLP. So it's interesting to look at them specifically, also in light of this BERTology cottage industry that I mentioned. So we're looking at pre-training of that, and then also looking at fine-tuning on sentiment analysis and natural language inference. So these are sort of core NLP tasks that if you work in NLP, you'll know about this. So the basic experiments that we do, so we're just interested in doing a comparison of different reservoir layers. These layers that are frozen. And so the baseline obviously is a regular transformer. So what that means is just multi-headed self-attention, and then this feed-forward layer. So in the transformer reservoir, what we do is we just have the same layer, but instead of updating it, we keep it fixed. But we also look at this feed-forward reservoir, where we don't apply the multi-headed self-attention, because if you keep that randomly initialized, if that has a bad initialization, then your attention mechanism is always going to be broken. So it might be better to just have a random projection without actually doing this attention. And we also look at convolutional neural networks and bidirectional gated recurrent units. So that's in the appendix. And we actually find that this idea also works for those types of layers, but maybe not as well. And we also look at different freezing strategies in the paper. Sort of just have to go through a bunch of the preliminaries that we did. So one question you might have, for example, is which layers do you freeze in the network? So we've explored this too. And we found that if you alternate, that works by far the best. So rather than having multiple consecutive frozen layers, what you want to have is freeze one and then have a non-frozen one and then freeze one and then have a non-frozen one. So alternating in your freezing strategy. So going to the results. So this has a bunch of plots here. So I'll just sort of talk you through. This is IWSLT, this is WNT, and this is Wiki 8 language modeling. So in these two, the metric is the blue score, so high is good. In language modeling, the metric is the bits per character, the bit rate per character, so low is good. The blue line is the regular transformer, the green line is the feed-forward reservoir, and the orange line is the transformer reservoir. So what we see here is that across multiple different configurations of the number of layers, either in the encoder or in the decoder for the language model, you see that these networks have a better AUCC than the actual transformer. So this is good. That means that they have a better compute performance trade-off on the validation set. And then if you look at test set performance, surprisingly, actually, because if you recall, we set out to do this in order to hopefully not have too much of a performance sacrifice when we speed things up. We actually find that this generalizes better. So that was a very surprising finding for us because you can be more efficient and actually perform better, so do less compute. We find something similar here, as you can see in language modeling. So on validation, better AUC and a better test set BPC. So that is a very nice result to see because that actually means that this helps. So this is over 3 different seeds, and so the error bars here are just the standard deviation. So digging a bit deeper on one thing in particular, if we look at the IWSLT results, we can really look at performance across different layers. In order to have this comparable, we always freeze 2 layers. And then you can look at interesting differences in, for example, the maximum blue score. So what you can see is that as the network gets deeper, then your blue score maximum actually becomes better than the real transformer, while your train time is much less. So this ratio here is the train time that you see compared to the train time that you would have seen in exactly the same configuration with the regular transformer. So you can get up to 21% improvements just by applying this trick. And of course, you have fewer parameters, which means that you have less training time. So this works really well. We also compare it to a very strong baseline of layer drop, where they do dropout essentially on the actual transformer layers so that you become more layer agnostic in a way. And that's also a way to speed up the computation, of course. And this works better than that. So that's also good to see. So moving on to mass language modeling. So in mass language modeling, you are interested in the perplexity on this large data set, right? There isn't really a validation set, it's just like a perplexity on your training data. So we looked at this for Roberta, and what we found is basically there isn't that big of a difference if you look at the perplexity. So this is, again, what you would like to see, where if you have some of these layers frozen, doesn't really matter for your overall perplexity on your pre-training task. But when you do the fine-tuning, so in this plot here, we show what happens when you do fine-tuning of different models in their pre-training phase. So during pre-training, you can see that this performs much better than the regular transformer. So you can really get substantial point improvements while being more time efficient. So up to 25% time savings to get better pre-training performance. And so the same is the case for different numbers of layers. Like a regular Roberta model would be something like 12 layers, right? And if it's smaller, then the gap is even bigger, where you can clearly see that the fine-tuning performance is also better for these models. We explore different versions of this. So you can either freeze everything. So you can either, when you fine-tune, you can freeze the layers that are frozen in your reservoir, but you can apply the same trick to a regularly trained transformer and then freeze them when you fine-tune, right? So this would be a strong baseline. And that works a little bit better, but still does not work as well as the reservoir approach. So one interesting thing we looked at, I mean, if you actually know what these are, then I would definitely encourage you to look at the paper. But we look at different probing tasks. And so these are supposed to measure syntactic phenomena that are present in your model. So has your model learned what the sentence length is? Has it learned to predict that? And so that's very interesting to look at, because people are trying to figure out if BERT learns the NLP pipeline, for example. There's a famous paper that claims that that's the case. And what we show here is that these models learn a lot of things, but if you look at the frozen layers, they actually appear to be better on these probing tasks than their non-frozen counterparts. So that's interesting, because they don't actually learn anything, right? They're frozen layers. So I think that has interesting repercussions for the study of Bertology, because it basically means that a lot of these experiments we maybe have to take with a grain of salt, or at least we have to be careful as a community to not overclaim the findings with this sort of stuff. All right, so the summary of this work is, if you train faster for shorter with fewer parameters, you get better results. So these reservoir layers, they improve efficiency, and they appear to generalize better on a bunch of different tasks of different sizes and different applications. So that's very neat. I think the explanation for this, actually, when you think about it, is just that noise often helps in generalization. So this is sort of a well-known finding, right? And in this case, because we're stacking layers in alternating fashion, if there's detrimental noise, then the really bad stuff can be removed by subsequent layers. So that means that you're adding noise, but the really bad noise is probably not going to hurt you too much. So that's a nice way of thinking about why this could work. Obviously, in addition to all of the prior work in the machine learning literature that says that this should not be too bad. So the way I like to think about this is as a way to add cheap additional parameters. So if you have more parameters, often with neural nets, they work better. So this is a very cheap way to do that in a way where you're maybe going to generalize better. So the final thing I wanted to talk about, and the final thing we do in the paper, which I'm very excited about, is we know that you can do this forward freezing, but when we do the backward pass, we still have to do the full computation, right? So we have to compute the gradients all the way to the bottom, and this is still expensive. So we're saving on the matrix addition that we would have to do here. So this is the gradient application, but we're not saving on the matrix multiplication that we would have to do in order to compute the backward pass. And an interesting idea is that you can actually just completely skip the backward pass at that layer and try to infer the gradients. And the way to do that is by just computing their expectation. And so using these expected gradients, you can maintain the backpropagation chain, except these are not the true gradients, but just the expected gradients. And if you do that, that will allow you to have even bigger time savings. Just about that expectation real quickly, I mean, I'm sort of abusing notation here, right? But the basic idea is that you, if you're familiar with reinforcement learning, you'll know what this means. We just take a Monte Carlo sample and then apply the likelihood ratio trick. So basic reinforce, but then on this this kind of continuous Gaussian. So in modern terms, this would be a continuous action policy gradient, and the reward in that case is the negative upstream gradient or loss. So essentially, we want to maximize the reward, which means that we want to minimize the loss if that loss is your reward. So I think this is a very clean idea. It's still a bit preliminary, but if you look at this table here, it works quite well. So it does not work quite as well as the transformer reservoir, but it does work better than the normal transformer, which I think is already in itself fascinating, that you can have approximate gradients and have it work better than having the real gradients and applying them everywhere. And of course, you can do so in a much faster way. So your training time is much lower, which I think is very neat. Future ideas, what I think would be cool to do with this stuff. So if we can have more work on backskipping, I think that's a really interesting direction to explore, not having these real gradients, but having inferred gradients, doing lottery ticket hypothesis stuff with reservoir layers. So if you've heard of the lottery ticket hypothesis, it's basically that some initializations are better than others. So maybe there are random projections that are automatically better than others, and if we can find those, maybe we can keep using them everywhere. So maybe we can have the same lottery ticket reservoir that we always intersperse in these networks, which I think would have interesting benefits for things like distributed training, where you can do massively parallel training of these elastic pipelines, as they're called, of batteries of GPUs. And another interesting application, of course, is doing hybrid hardware implementations of this, because if you don't have to do a backward pass, especially if you don't have to do a backward pass, you can have, and I guess that's also one of the purposes of this meetup, you can have very fast computations, right? So I guess at light speed, but I'm not an expert, so I'm very interested in hearing more about that. So in conclusion, GPT-2, which feels prehistoric by now, already had 1.5 billion parameters. Now we have models that are exceeding 1 trillion parameters, and I think soon this will become the new normal. So what this is, if anything, is just a way to add cheaper parameters, so you can scale further in a cheaper way. And so what this is showing is that will actually work. So it's worth exploring, I think. So it's a simple idea. It works really well, which means it's probably never going to be accepted at a real conference, unfortunately. So at iClear, we got very unlucky with the reviewer draw. So yeah, that's always the story with papers like this. But I'm personally very excited about this because I think it has lots of potential applications. So that's me. Thanks for listening.
Thank you for the presentation. It was very clear and interesting. I was familiar with most of the literature. I didn't know about the Gamba perceptron. That's super curious. So I learned something. Yeah, and as you were saying, there are a lot of topics that actually overlap with our interests at LightOn. So now it's the time for questions. I guess people from the team will have questions for sure. If you have questions, you can either unmute yourself. I think you are allowed to do that. Or if you prefer, like if you're in a noisy environment, you can write them in the chat and I will ask them for you. So any questions? I see Ruben has a raised hand. Go ahead, Ruben.
Hi, thanks for the great talk. So I'm very familiar with reservoir computing, and I was so I don't really understand your architecture in the sense that you freeze some layer, right? So there is no recurrence in the sense that reservoir computing is based on recurrence. So I was wondering if you
could... So I guess if you're a purist in the reservoir computing literature, then you would maybe say that that is not really a reservoir, because it doesn't have any dynamics of its own, right? I guess is what you would expect with an RNN. So we did do this with RNNs too. It just turned out to not work as well as transformers. So we did bidirectional GRU, so RNNs but with some gating, right? And we found that it works there too. And so would you consider that a reservoir if it was an RNN?
Yes. Okay. Yes, exactly.
So I think so. We tried that too, but so it's just transformers are better than RNNs. Yes,
of course. But I was just wondering, in your architecture, so it's basically a random feature that you put. It's
so it stays random, right? So a lot of people, so there's been a lot of work in trying to freeze them, like sometimes, and then sometimes updating them. But so in this case, they just stay random all the time.
Okay, perfect. Thanks a lot.
Other questions? I have some, but I'll keep them at the end. Julien?
Yes. First, well, thank you for the presentation. I think it was very interesting. In particular, I'm very interested in the backskipping concept. I do mainly work on like alternative to backpropagation, so I'm always interested in seeing like approximated scheme. I'm not very familiar with the reinforce that you use for approximating the gradient. So maybe what I'm about to say is not good. Like, is it more expensive than doing like a matrix just a single matrix multiplication between the dimension of between the two dimensions that you have, essentially approximating the backward with like a random matrix? You know, it's an idea that you maybe have seen in the literature as feedback alignment or that kind of thing.
Yeah. So I guess that depends on how big the layer is, right? So in this case, we're pretending that it's just a linear layer, but it's actually a transformer layer, right? So that is computationally much heavier than just a single matrix multiplication that you have to do in a backward pass. So if I can see your point that if it's just one single layer, then if you do reinforce, you have to predict the gradient. So that is also a single matrix multiplication, right? From your so I guess in a sense to compute your policy. And so in order to compute the policy, you need to do that matrix multiply too. Yeah, but so a transformer is more than just one single matrix multiply.
Absolutely, yeah. I think you will probably be very interested in. I think you would get, from my understanding of reinforce, I think it will not be more costly to approximate the entire actually like transformer block in the backward as just like a random matrix. Like just take the gradient that you have coming in, multiply it by random matrix to make it match the dimension if they are different, or just to mix things up. And I think this would work actually because we do that kind of stuff. We train transformers in this way with what's called feedback alignment or direct feedback alignment. And we have found like not only it worked, but we have found ways to make it work like actually almost as well as backpropagation at like the full training the entire transformers like that. So it's quite, I think it's quite interesting, and actually you are pointing is very similar. So it's super cool to see this idea of changing the backward spreading everywhere. This is super nice.
Very cool. Yeah, I would love to have papers about that. If I search for feedback alignment, I'll find them. Or
yeah, actually I will. If you search feedback alignment, you will find it. But I can send you an email afterward if you want with this.
Sounds great.
Thank you for the answer. Martin, I see you have a raised hand.
Yeah, hi. Also, thank you for the talk for me. I'm also very intrigued by the backskipping, and especially the possibility to implement that or hard code that in hardware, like a random circuit, for example. I think you proposed in the paper. Is there anywhere where we can read more about backskipping?
Yeah. So I mean, it's one paragraph in the paper at the end, and so I think initially, so that was basically the idea we started with. And then we found all of this other stuff that already worked. So then we decided to write a paper about that, but also just have some preliminary results about backskipping. So we're still exploring this. So we might do another paper about this later. Especially, so what I am personally interested in is this lottery ticket thing as well. So if you could actually have the same projection always be useful everywhere, and then skip the backward pass for all of these layers, then I think that could really have pretty dramatic improvements. But the idea is very simple. I mean, if you guys want, I can send you the code. It's like 5 lines.
Okay, yeah, that'd be amazing if I could send you an email and maybe you can help me out. Thank you very much.
Thank you. Other questions?
Yes, me again. Sorry. So I don't know much about transformers, but I know that Koromansky for Google Brain has the performer. It's like random features, but with structure transforms. So the architecture, the way they put their random features is different from your work, right?
Yeah. So that work came out later than I think ours, or so because ours was submitted to open review quite a while ago, right?
Okay.
But so what that paper does is there's a whole literature now on doing faster approximate self-attention, right? So they're just so essentially that's quadratic, which is expensive, and you can do it linearly by just doing a low rank approximation. And that is the idea that underlies a lot of these different methods. And the performer is I mean, I guess you guys all know about the power of random projections. So it's just like the random projection way of doing a low rank approximation.
Yes. Okay.
So in this case, we're doing the whole layer, right? So they're really focusing on making the attention mechanism more efficient by doing this low rank thing. And in our case, we're saying you don't even need attention in some of these layers. You just need a random projection.
Oh, okay. Okay, perfect. Thank you.
Thanks. Martin, you still have a raised hand. I don't know if you have another question or it's the one from before. Okay.
Sorry, it was one from before.
No problem. Yeah, anyone has another question? Otherwise, I'll start asking mine. Okay, I'll go with one. This is pretty easy, actually. It's just when you show the training time and you show that with the reservoir transformer it's faster. Like, what instance of the various configuration was this specifically? Like, were you doing backskipping there? Which layers were frozen and how?
So are you talking about a specific? Let me just
At some point there was a table with
this one.
Yep, this one.
Yeah, so this is without backskipping. This is the
Okay.
the regular thing. There's 2 frozen layers. They're always the 2 in the middle.
Yeah, and so here, where does the gain come from? It's just from the fact that you don't update the layers, so the weights, and it's this substantial. Like, I'm
Yes.
quite amazed by how
Yeah, me
substantial
too.
it is just by not doing this.
Yeah, so just not updating, right? It almost feels, that's why, I mean, I said in the talk, it's sort of an embarrassingly simple idea, right? And so
Yeah.
People will think it's sort of stupid maybe, or too easy, but it actually works really well. So and these are substantial improvements, right? And this is across different seeds on exactly the same hardware. There are different machines, but so as you can see, like the variance isn't that much anyway. So
yeah, and I'm thinking that yeah, as you mentioned, GPT-like architectures, of course, when you scale it up, it also becomes an issue in terms of memory, having all these weights and their average history.
yeah, so we have a number somewhere in the paper actually where we say, like, so if you extrapolate this to a GPT style computation, then you save, like, I don't know how much it is, like 1 week.
Yeah, and so this is my second question. Like from this talk, I got maybe 100 different ideas on how this could be used to scale up distributed training of these kind of models. And like, because the main issue there is, well, first of all, well, the engineering effort of building the hardware to do it, and then it's communication cost and this kind of stuff, right? And there are many ways of leveraging this to make it simpler. And I was wondering if you already thought about like kind of a plan to do this, like what would be the thing that makes the most sense to you?
Yeah, I mean, I'm talking to a couple of different teams internally about exploring this. So there's this paper. I mean, I don't know if I can even give you the title, but there is a paper coming out soon. It's being submitted to ICML that uses this idea for doing elastic pipelining for distributed transformer training. So I think, yeah, it's sort of an obvious thing to try there. And so, I mean, if you have some sort of caching mechanisms and you can just use your random layers in a smart way, then that will help. Yeah.
Yeah, that's super cool. And the other thing I was thinking is this is actually pretty useful for like what's called heterogeneous computing, because one of the issues of this kind of system is that if you have all GPUs and you want them to communicate fast between each other, well, NVIDIA builds a solution because it's their business. But when you have different hardware from different companies, well, the intercommunication is actually a bit harder because who takes care of that, essentially. And instead, with this kind of work, well, if you can skip the layer in the backward, the communication cost is only in the forward, and so the thing becomes cheaper. So, well, it's not free, but since the backward is usually more costly, it's maybe 1/3 of the total cost that you had before. So, yeah.
And I guess so. If you find these lottery tickets, then you can really just hard code them in your thing, right? Which makes it very cheap to make them. And then I guess you could have like a part of a neural net live on a GPU, and then if you can offload that onto these very fast, maybe optical forward passes, and then not have to do the backward pass. So basically go straight back to the GPU, then that could be very fast, I think.
Definitely. Yeah, I've run out of questions on my end. Does anyone else have any other question? Yeah, Martin, you have your raised hand again.
Maybe this will all get clarified if Douwe can send me code or something. But for the backskipping, do you not have if I understand reinforcement learning right, you need some kind of exploration phase at first before you get sensible predictions out of it. Is that factored into those improvements that you get in training?
So I guess what you're saying is, so the exploration you do naturally, right? But what you're worried about is that during the exploration, you will learn bad things because you don't have a good policy estimate yet. So the way to do that is you can anneal. So basically, you want to start with the real gradients and then learn a value function, which is sort of like a baseline in reinforcement learning. And this baseline predicts the real gradients. So as soon as that prediction becomes relatively stable, then you can use this in your reinforce.
Oh, okay. So initially you do real. Sorry, go ahead.
Maybe I can just show you in the paper. So basically, what you're learning is some policy, right? Where you want to predict these mu's from which you sample, right? So this is your continuous action reinforce thing. So what you want to learn is this value function as a baseline. And if that value function is good enough, then this will stabilize your samples, right? So initially, if you do reinforce, it's going to be super high variance, and this value estimator is going to reduce the variance substantially. So what you want to do is first have a reasonable value function, and then after that, you can slowly anneal where you just backskip all the way. So initially, you don't backskip. that much, right? So you anneal the probability of backskipping instead of doing a true backward pass. And so slowly you will start backskipping more and more until you only backskip.
Okay, that makes sense. Thank you. That helped.
Thanks. And any other question? I don't see any raised hand. So yeah, I think we can close it here. And I want to thank you again for a great presentation and the discussion. It was really insightful. I guess Julian will be in contact with you to discuss the backskipping. And yeah, we are gonna post the video on our YouTube channel, and also I'm gonna write a blog post summarizing the talk. It will be out tomorrow probably. That was great. Thank you again, and well, I guess have a nice day.
Yeah, have a nice evening. Thanks for having me.
Thanks a lot. Bye bye.
Bye.